So officially, good afternoon to everyone. I'm Matej Feder from the Nation Company, and today I'm here to talk you about how we monitor our infrastructure, which consists of multiple Kubernetes clusters, multiple OpenShift clusters, as well as multiple virtual machines and physical nodes, all managed from a single place we called the observer cluster. So let's start with our motivation. We aim to achieve a global view of all our infrastructure components, meaning we wanted to visualize our all relevant infrastructure metrics in one Grafana deployment. Additionally, we wanted an effective alerting system to notify us when certain metrics exceed defined thresholds. And in addition, we wanted to be informed about any issues with our infrastructure and investigate these alerts from a single location. So to achieve this, we went through several iterations, including uh, experimenting with Elasticstack and Kibana, testing Kubernetes distributions that offer built-in monitoring solutions such as Rancher and OpenShift, and seeking inspiration from them. After several iterations, we decided to use Prometheus in conjunction with the Thanos stack. If you are familiar with Thanos and Prometheus, you know that Thanos allows you to have a highly available Prometheus deployment, and there are some additional features like downsampling, uh, compacting of your metrics, long-term storage in your Bitbucket or in your object store, and so on and so forth. This slide shows a high-level overview of our global view solution. You can see observer cluster on the left side of the slide, which contains the Prometheus Thanos components along with the visualization layer. So only in our infrastructure, in our observer infrastructure, only the observer cluster contains the visualization layer. It means the Grafana. You can also see our infrastructure endpoints that the observer cluster can scrape. We have also been experimenting with the Prometheus remote drive feature, allowing some endpoints to send metrics to the observer's remote drive endpoint. So let's take a closer look at the observer components. For simplicity, I have divided the observer cluster components into two layers. The first layer is the... Wait a moment, I say to my colleagues that I have a presentation. Okay. So the first is a data layer, which includes software that collects and stores observability data, such as and there are components such as Prometheus and Thanos for metrics, or Loki for logs. And then we have the visualization layer consisting of Grafana and Grafana dashboards we have developed, which we refer to as the DNation Kubernetes monitoring project. So we developed batch of Grafana dashboards, and we wrote a bunch of Grafana dashboards into a JSONet, and this project we called DNation Kubernetes monitoring. The visualization layer, and the reason why I divided the observer into these two layers, is that the visualization layer can theoretically be used in conjunction with other data layer components that are compatible with Prometheus PromQL language. It's important to note that we haven't yet tested the visualization layer with another PromQL stack, but there is a good chance, I would say, that the dashboards we developed could be used with, for example, Victoria metrics as a Grafana data source. As far as I know, Victoria metrics has a overlap with PromQL about 80% or something like that. Now let's dive a bit deeper. So this slide summarizes the observer software components we currently use. As you can see, the visualization layer contains just 3 components: Grafana, destination monitoring containing the Grafana dashboards, and Prometheus rules written in JSONet language. We also have a JSONet translator that converts JSONet to formats readable by Grafana and Prometheus. And the data layer includes multiple projects, all of which can be deployed using a single one we maintained. This umbrella Helm chart is called the Nation Kubernetes Monitoring Stack. It can deploy other components such as Prometheus operator, alert manager, various Thanos components, Loki for logs, and various Prometheus exporters and service monitors, and so on and so forth. So a lot of things could be deployed to it only one umbrella chart. We maintain this umbrella chart and we keep it up to date. From my point of view, the real or the main added value we have developed is the nice visualization layer. You know, we have invested a lot of time in Prometheus, Thanos, and data layer and similar components. However, these components are well known, and you can easily find many useful tutorials and blogs about how to use and deploy Prometheus, Thanos, Loki, and so on. But if you wish to view metrics from multiple infrastructure components, this becomes a challenge, as there is not much open source code available for this purpose. It means often the visualization part is proprietary and requires payment. So we began using dashboards from Kubernetes mixing project, but we soon realized that we desired something more intuitive and informative. So we wanted to open our Grafana and immediately see what is wrong with our infrastructure. As a result, we decided to create a set of dashboards defining 3 design principles that our product aims to achieve. So we developed our dashboards in the way that our dashboards should be intuitive. They should display only relevant information. And if you want to see more details, you should click and drill down deeper into the lower level dashboards, which will provide you with more information and actual metrics and dashboards with metrics. This slide illustrates the drill down design principle we have implemented. Initially, you see the layer 0 status panel for one of our Kubernetes cluster, displaying only green panel with a string OK. So everything looks good. Then you can click and drill down to the next layer, layer 1, where you will find additional Kubernetes related panels and statistics. If you wish to access more details, you can click and click again and drill down to the layer 2. finally you can reach the actual metrics in the bottom layer 3, if you want. Of course, all these dashboards are available in Grafana, so you don't have to drill down and click. If you don't want to do that, you can directly access the dashboard you desire via the list of dashboards panel in your Grafana. So it depends how you are familiar with the technology you use in your infrastructure. For example, if you want to observe Kubernetes clusters, you have to know that there are some control plane components, and if you want to see some control plane components related metrics, you have to find the relevant dashboard for this control plane component metrics. So could be challenging to find it. Because of that, we also use this drill down principle. Next, with our observer cluster and the monitoring solution, we have that we developed. We are using. We can observe multiple endpoints. For example, as I said, Kubernetes clusters, OpenShift clusters, but also virtual or physical hosts and machines, and applications that run on these hosts or within Kubernetes of OpenShift clusters. This means we have base dashboards for Kubernetes and OpenShift clusters, as well as for hosts, and some application-specific dashboards that can be assigned to particular cluster or host. You can see some examples in this slide. As you can see on the right side, all these dashboards are defined in the YAML files. So if you want to register another endpoint, another host, another application, another cluster, you have to just adjust the YAML file and deploy our monitoring solution, and that's it. Oops. And the last slide about the visualization layer is just for an information purposes. The dashboards written in JSON are highly customizable. So this means that the thresholds we defined as a reasonable defaults, all these thresholds can be overridden. Also, you can override the structure of the dashboards, colors if you want, and we used as a default. So basically, you can override everything, but there are some recommendations from our side in our documentation of what is good to override and what not. That's it regarding the visualization layer. And to ensure we have a complete understanding, let's briefly discuss the architecture. In this slide, you can see two proposed architecture diagrams that we discussed in the SCS SIG monitoring meetings. In summary, there are two distinct architectures, one dedicated to infrastructure and another one focused on Kubernetes as a service offerings. The one designed for infrastructure located at the bottom employs a pool-based model, meaning that the observer cluster pulls metrics from various infrastructure components. So the bottom one, this architecture is internally used by the nation company and works. So we have we have a proof that this is working, and we are using this architecture on daily basis. The architecture displayed at the top of the slide has been proposed as the architecture for Kubernetes as a service offerings. In this context, cloud service providers offer Kubernetes as a service and aim to monitor the Kubernetes clusters they create for their customers. So this architecture uses remote writes, meaning that the Kubernetes clusters on the right side writes metrics to the observer cluster. Additionally, as you can see, the lightweight Prometheus agent is used instead of Prometheus server here. So this solution, or each solution offers distinct advantages when compared to the other. For instance, the pool-based model is more straightforward, widely used by many Prometheus users, and doesn't require as complex infrastructure as a remote write approach here. Oops. On the other hand, the remote write approach we proposed for Kubernetes as a service offering uses a Prometheus agent, so lightweight alternative of Prometheus server, and in my opinion, this solution or this architecture is more dynamic in comparison to the pool-based architecture model. So very well suited for the use case we have, which is Kubernetes as a service offering. So that's it regarding the slides and the very briefly overview of our visualization layer and the architecture we proposed and we use internally in DNation. Now, I think if you are not any comments or questions regarding the slides or the architecture, we can move forward and show some demo, maybe.
Okay, then maybe let me ask if there are already questions regarding the architecture or slides or the content you provided before we go to the demo.
Yeah, sure.
I have one, but I think that one is better for the discussion later on. So
there is a question from Matteo in the chat. Could you elaborate on object store? What object store would you use at scale? So internally, we are using MinIO as an object store, so S3 compatible bucket. Thanos could write your metrics to the wide to the lot of object storage, or I guess. So not only to the S3, also as far as I know, Swift is also supported, and a bunch of others for sure. So basically, we are using MinIO. In the context of SCS, we plan to use Swift, but the S3 compatible API of Swift. And that's it from my side regarding the object store. If you have any additional comments, questions, let me know. Kurt?
yeah, I do have a follow-up question. And actually, I guess in the SCS context, maybe to comment on what you just said, the standard approach we're normally using is that we're using Ceph storage and then use Rados gateway to provide both Swift and S3. So technically it's not Swift that you use then. But one quick question: if you're trying to observe your infrastructure, I guess you would want to use S3 or some other object storage on a different infrastructure to make sure you kind of have the observation data in case something goes wrong with your infrastructure. Is that something you would do, or is that something you don't typically consider in your observer cluster?
Sorry, could you repeat your question, because I just read the messages very quickly.
I was wondering if you use your observer cluster to also detect issues with your infrastructure, then maybe the object store from your infrastructure will not be available in case there's trouble. So I guess you can write to object storage on a different infrastructure, right?
Yes, for sure, for sure. I would say that the best practice is to not have the object store within the same cluster as you use for the observability. So the recommended scenario is to use another cluster if you use MinIO like we use. So yeah, basically our setup is that we have a MinIO in one cluster, and another cluster is dedicated for the observability thing, like Prometheus and Thanos and Grafana. So this is the recommended way, but you know it's always depend on costs, and another cluster means another cost for your infrastructure. But the safer solution is to have a dedicated place for the object storage, or has some remote object storage for your long-term metrics. This is the recommended way for sure.
I guess the nice detail in SCS is that maybe Plus Server could save the logs from whatever WaveStack and vice versa. So we could help each other. But let's look at the other questions. I think Maya has one.
Mm-hmm. Does it make sense? Does it make sense to use Thanos for the observable clusters as well? For class clusters, I mean. Yeah, good question, Maya. So yeah, it is possible for sure, but we decided, or we proposed, to use Prometheus agent and not Prometheus server with Thanos sidecar, because of the footprint. So Prometheus server could consume much more resources in comparison to Prometheus agent, and this was the main reason why we decided to not use Thanos sidecar together with Prometheus server for Kubernetes as a service part of architecture. So I hope I answered your question. Mark has another one.
Maybe you read it out, Matej, so everybody.
Would it also be possible to provide the dashboards for different clients or users groups without having to provide the infrastructure multiple times? How could one? Okay, so okay, this could be the first question, I guess. So I think this question is about the multi-tenancy of this solution. So for Kubernetes as a service offering, and for this part of the architecture, we have a plan to investigate also the multi-tenancy, because the Thanos receiver component, which we use in the observer cluster for as a remote write endpoint, is multi-tenancy capable. So it is possible, at least based on documentation, and this is not addressed yet. and will be investigated and will be addressed. So this is way how we design these things, like multiple instances per Kubernetes clusters per customer, so multi-tenancy. The second one, how could one proceed if one wants the offer Grafana or the dashboards for different groups of users with different visibility of the collected data? Very good question, Mark, again. So, as far as I know, Grafana has also concept of multi-tenancy, but the concept of multi-tenancy in Grafana is based on the organization level. So there is an organization, and organization in Grafana context means the tenant. And it's for us, it's not so straightforward solution to use. We don't see this as a straightforward solution, so we don't see using of Grafana organizations per tenant as a solution. Instead, we got inspiration from the OpenShift project. OpenShift project uses some proxy project, which I forget the name of the proxy project. Some project which forces the labels to the queries. So in the middle of the Grafana and the Prometheus endpoint, you have some proxy, some kind of proxy project, and this proxy project forces the labels to your Prometheus query based on the user which sends this query using the Grafana. And this solution achieves some kind of multi-tenancy on the Grafana level. So I hope I will send the exact name of the project right after the presentation. Prom label proxy, this is the one. Thank you, Sven. Already in the chat. The last time I used Grafana in this use case, I was necessary to store the data in different data sources, and you had to manually assign the users to these different organizations. This did not work very well with the OIDC login. I think this is somehow related to the previous one. I hope I answered the all. Okay, thank you, Mark. I recognize your sign. Maya, there is some solution called Observatorium Mark for multi-tenancy. Okay, so this is another comments to your questions. And that's it, I think. That's it. I hope I answered all the questions from the chat, and if you have some another direct questions, raise your voice or raise your keyboard again.
Yeah, so we have this hand that can be raised that is maybe convenient to indicate. And you're very well invited to also use your mic and talk. Chat works as well, of course. Matej, you wanted to show us a bit of a demo, right?
Right.
Maybe it's a good time to go there now, and then after the demo, maybe there's some more questions and more discussion.
Okay. So I will share another. Maybe I will share my entire screen number 1. Hop. Okay, I hope you can see my screen right now, and you can read the one line here. If not, I can zoom a little bit.
Yeah, maybe you make the font a bit larger, Matej, then we can read it.
Works.
Looks good.
So basically, what I want to show you, let's briefly look at the presentation again. So this demo I have presented on Monday in the SIG monitoring meeting. So for those who attended this meeting, this is the same one I presented on in the SIG monitoring meeting at Friday. But basically, this demo is about the architecture for Kubernetes as a service offering. So on the left side, we have an observer cluster. So this is the left side of my screen, and you can see the main dashboard, the layer 0 dashboard of the observer cluster for Kubernetes as a service offering. As you can see, this is just for demo purposes, the Grafana for the demo purposes, but I hope it's sufficient for the demo. So this dashboard shows OK status and OK green status for the observer cluster itself. So it means that the observer cluster on the left side monitors itself. So as you can see, and also the layer 1 dashboard, the main dashboard shows you some basic counters. So you can see that right now we have only one Kubernetes cluster is in a OK or in the healthy state. We have 0 in the warning and also 0 in the critical state. And this dashboard was proposed just for Kubernetes as a service observer version of our monitoring solution, and the rest is the same. So if I click to the layer 1 rectangle, I drill down and visit the next layer dashboard dedicated for observer cluster. Again, there are some alerts, basic counters here, and there are some control plane dedicated rectangles, which if you are familiar with Kubernetes control plane, you can see some etcd, stats, kubelet, proxy, and so on. There is also some overview for nodes, stateful set pods, jobs, which the observer clusters utilize. There are also some dedicated sections for control plane nodes and for worker nodes. And again, if you want to see some etcd dedicated metrics, you can drill down. And if you want to see some, for example, master or control plane nodes dedicated system metrics, you can drill down. You can see the CPU utilization, drill down, and you can see CPU, memory, disk, and all this stuff if you are familiar with node exporter. So these metrics are collected from a node exporter deployed in the one of the node in the observer cluster. So basically, the observer cluster is up and running. It observes itself, and this is the 0, 1. Oh, the layer 1 dashboard for the Kubernetes as a service solution. On the right side, I have a terminal, and this terminal is SS via this terminal SSH to the virtual machine, we deployed just for this demo. This virtual machine should mock or fake our Kubernetes as a service offering. Basically, this virtual machine has 16 CPUs and 64 G of RAM, as far as I know, and there is a script. There is a script kas.sh, and this script should mock Kubernetes as a service offering. As you can see, this script basically, based on the parameters, runs this function. So overall, this script creates multiple Kubernetes clusters in a kind environment. So we use Kubernetes in the Docker for this demo, and the script creates multiple Kubernetes clusters in kind in parallel, because the parallel command is also used here. And these kind clusters, after each kind cluster is created, it is bootstrapped with Prometheus in agent mode. So this Prometheus in the agent mode is deployed to each kind cluster, and then the Prometheus in agent mode remote writes all the metrics collected from the kind clusters to the observer on the left side. So that's it regarding the script and the setup for the demo, and let's execute it. Maybe time. Yes, let's create six kind clusters, and let's see how these kind clusters are then registered, or not registered, but how these six kind clusters sends or remote writes the metrics to the observer clusters. And this operation or this deployment takes approximately 2 or 3 minutes. So in the meantime, we have some time for further questions or discussions if you want.
I see no questions in the chat, but maybe somebody wants to speak.
So basically, you can right now you can see in the terminal that some number 6 kind clusters are going to be up, and after this procedure, all these 6 kind Kubernetes clusters will be bootstrapped with Prometheus agent. Basically, we used Prometheus operator for this bootstrapping, so maybe I can show you in the meantime project. You can find all this configuration stuff. So there is a Kubernetes observability project in Sovereign Cloud Stack GitHub organization, and all this stuff, all the configuration YAML files and script. I show you. You can find it here. So maybe I will send you this link to the chat. Okay. It seems that some of the clusters are up based on the log messages I see. And right now, as you can see, some of those clusters also are bootstrapped by the Prometheus operator and Prometheus agent. So 2 minutes and something. Great. So you can see, for example, right now the context is set to the kind Kubernetes as a service cluster number 6. So you can see the Prometheus agent is not ready yet. And right now it's running, at least in the Kubernetes as a service cluster with number 6. And after some time, I hope that we will see some new rectangles on the left side. Let's wait.
Meanwhile, we do have a question on the chat, Matej. Weil is asking, what about data transfer cost between the agent clusters and the observer? Are the costs high, since data transfer between different VPC could be very expensive?
Mm-hmm. That may be true, could be true, but basically this solution was proposed for as a solution for cloud service provider that wants to observe Kubernetes clusters that are deployed within cloud service provider infrastructure. So in ideal scenario, there will be only one infrastructure, and the one infrastructure, the infrastructure which is owned by cloud service provider, which offers this Kubernetes as a service solution or offering. So I hope I answered your questions, that we don't expect that there will be some data transfer between multiple clouds, let's say. In the meantime, as you can see, all 6 clusters on the left side are up and have a green status with OK string. So I can click, for example, to the number 3, and for example, containers. You can see that there are some up and running containers. Again, database. Oops. And we can see that some metrics are already there in the observer cluster, CPU, network, and so on and so forth. Last 15 minutes. Okay. And that's it regarding the demo. This is the demo is in the very beginning iterations. So we expect some improvements in the near future, for sure. Main issue which we have right now is with alerts which we deployed in the observer cluster. Alerting doesn't work well right now with this architecture, but this is something which we know and we will improve in the next MVPs. Can you quickly simulate a failure? Yeah, this is which is not working right now because of unworking alerts right now. Will be addressed in the near future. But for example, the main issue which we have with alerts right now if I right now destroy some Kubernetes cluster on the right side, then it disappears on the left side. So this is the main issue we have. But if I just partially destroy some elements in the Kubernetes cluster on the right side, it should work, I think. Maybe. Okay, get what's maybe I can somehow destroy something. Kube proxy, maybe. Proxy is deployment. Wait a moment. Coordinates, okay, coordinates. I will try to just define some image which for sure doesn't exist. Maybe we will see. So right now we have some failure here. As I said, the arting doesn't work right now, so let's investigate the failure in this way. Last 5 minutes. And let's wait. Okay, so right now we can see 99.9% of running containers and pods. It's a good sign that something works. And yeah, coordinates, waiting error image pool. There is some visibility without alerts right now into our Kubernetes as a service offering. So something on metrics level works, but we have some issues with the alerting right now. So basically, this should trigger in normal situation. This should trigger also the alert and potentially send the observer server should send this alert to some chat or email or something. But this doesn't work with the Kubernetes as a service architecture, and but for sure it works in our internal architecture, which was discussed and is on the bottom of this slide. So the arts are working here, but currently not here. And that's it. Nice overview. Thank you, Benjamin.
Okay, so we only have a few minutes left. Thanks for the presentation. And maybe to start the second today, maybe short part, I stopped the recording right now. Give me